I want to spend a few minutes today talking about some evidence to support Maxwell's theory of EMR. Not this whole four wave properties that support the wave nature of it, but we're talking about empirical evidence, experimental evidence from an experiment that was done to support the Maxwell theory of EMR. Well, a guy named Heinrich Hertz, you should remember his name, right? We've seen his name since Physics 20. Hertz is the unit for frequency. It's not a coincidence that's the unit for frequency, and Hertz was the guy who performed experiments with EMR to verify Maxwell's theory. Hertz used what we call a spark gap apparatus. I'll explain what that means in a second. He's the spark gap apparatus, which essentially accelerated electrons across a little gap, and then he used an antenna to detect the electromagnetic radiation produced by that spark gap apparatus, by that electron accelerating across that little gap. Here's what the apparatus more or less looked like. Just hold off before you draw this, okay? I'll pause and give you a chance to draw this yourself here in just a couple minutes. We have what we call a step-up transformer. In Physics 30, we used to, prior to 2007, learn about the details of a transformer. We learned how a transformer functioned, the details of it. We don't do that now. Just now, I'll just tell you, and you're going to have to trust me, that a transformer can change a current or a potential difference to a higher or lower value. This is what we call a step-up transformer. It changes a potential difference to a higher value. So if we start off with a low potential difference over here, then we end up getting a high potential difference over here. It's a step-up transformer. You can see that on the what we call the primary side here, we have what we call an alternating current, an AC current. Okay, that would be the symbol for an AC current versus this, which would be the symbol for a DC battery, a direct current. This alternating current power supply causes an electric current that oscillates, that goes back and forth, back and forth, back and forth. And this step-up transformer changes the potential difference that's produced over here on the left-hand side, the primary side, to a higher potential difference on the secondary side. We want a big potential difference on the secondary side because on the secondary side, you don't have a complete circuit. You got this little gap right here, this little gap in the wire. And if you got a low potential difference, then the electrons aren't going to go across that gap. They're going to stop when they get to the ends of the wires. But if you got a big potential difference, it's kind of like lightning, right? You got a little potential difference between the cloud and the ground, electrons don't go. But if you got a big potential difference and humidity in the air, then electrons will jump the gap from the cloud to the ground. If you get a big potential difference here, electrons will jump across this spark gap. So that's why we put the big potential difference there. Now, as they jump across this spark gap, understand that they were not moving, then they're jumping across the gap. So in that process, they must accelerate. Okay, this isn't a Maxwell thing at all. Okay? Charged particles that are jumping across the gap that weren't jumping across the gap before must accelerate. Now, what Hertz said is that if he can detect EMR right here in this antenna, then it must have been those accelerating charges, those electrons jumping across the gap that produced EMR. Right? If you have this system isolated and controlled for all the external factors, and you didn't have EMR detected in this antenna before, and you do have EMR detected when electrons are jumping across the gap, then it must be the accelerating electrons that are generating the EMR, if you detect EMR in this antenna. Now, how do you detect EMR in this antenna? Well, if EMR consists of a changing electric and a changing magnetic field, as Maxwell said it did, then that changing electric and changing magnetic field should generate, because EMR consists of a changing electric and a changing magnetic field, it should generate an electric current in the antenna. All the antenna is a conductor. If you can measure an electric current in the antenna, then there must have been a changing electric and magnetic field. And if there was a changing electric and magnetic field, it must have been caused by the accelerating charged particle. And that's exactly what Maxwell told us, right? It's exactly what he hypothesized. Accelerating charges generate EMR. EMR consists of a changing electric and a changing magnetic field. So if he detects an electric current in this antenna, then Maxwell's theory must be right. Guess what? He detected a current in the antenna. So Maxwell's theory was just experimentally verified by Hertz. We had an accelerating charge that produced a changing electric and magnetic field, which caused a current in the antenna. Now, this is the first type of EMR that was experimentally observed. He got to name it. Look, you discover something, you're the first guy to do something, you get to name it. He named them radio waves. These were really low frequency EMR. He didn't use gamma rays or X-rays or even visible light. Why? Because they're a lot harder to make. Radio waves, because the frequency is so low, are much easier to produce. He didn't consciously say, oh, I'm going to use radio waves for this. He just consciously said, look, I'm going to use a pretty low frequency thing. He named that low frequency thing radio waves once he actually detected them. There's a few questions that I want you to work on for homework now on page 647. Those questions are, page 647, number 1 and 2. Number 5, 7, and 8 to 14. For tomorrow, please.